Hi, in this video, I'll discuss electric potential due to a point charge. So here's our definition of electric potential. This is V, so change in V equals the negative integral from some reference point, which is an arbitrary reference point, to the point where we want to find V. So let's write that. And this is the electric field E. In a moment, we're going to apply Coulomb's law because we're looking at a point charge, dotted with some path along which you take to get to that point. So let's discuss what these two things are. This is some arbitrary reference point. Now this arbitrary reference point is kind of like saying, what is the elevation of a city like Tacoma? Well, in order to say what the elevation of Tacoma is, you have to be on the same page about what sea level is. So you're saying the potential at some point with reference to an arbitrary reference point. In the case of elevation, we say sea level. In the case of potential, it may be different depending on the situation. You'll see in the situation we're about to do, we're going to choose V at infinity and assume it's 0 there. So we're going to from an arbitrary reference point to some point where we want to find V. Now this is, so let's write that. Change in V becomes V at the point minus V at the reference. Okay, so let's plug in some stuff that we know about this. So let's rewrite this as change in V equals the negative integral from, we're going from infinity to the place where we want to find V. So let's say it's a distance r away from a point charge. We'll draw a picture in just a moment. And the electric field away from a point charge is Coulomb's law, kq over r squared. And there's an r hat in there that represents the distance. It's a unit vector distance. Dotted with the path along which we have to take to get from infinity to some point r. So what does that look like? Well, some point charge q, here's our q, we're going to go from really far away, infinity, that's really far, into point charge q. And we come into point charge q radially. So in order to get from infinity to point charge q, we travel along the radius. That means that r hat and dl are parallel to one another. And so the dot product between these two really just becomes the path along which you have to travel, which is the radius. So it becomes dr, r hat, dotted with dl equals dr. And you know that a dot product, two vectors multiplied together, gets you a scalar. All right, now we can compute this integral. So we're looking for our V point minus V reference. Let's write that on the other side. It's V at point R minus V at infinity. The reason we chose V at infinity is because we're assuming that it's 0 very, very far away from this point charge. So really, this is 0. So VR is what the left side of this equation becomes, and that's equal to the right side here. Let's reduce it and take out the constants. Negative k and q is constant. And we're left with an integral from infinity to r of basically r to the negative 2. Okay, and the answer to this integral, r to the negative 2. Negative 1 over r, and we evaluate that from infinity to r, and what we get is kq. I want you to notice one thing about electric potential, V, is it's not a vector like E was. Remember that the Coulomb's law contained a vector. It also had r squared down here. It was a vector, but V, the potential, is not.